Hi, everyone, and welcome to our webinar today. My name is Paul Bemis. I'm going to be your host and going to be reviewing the material. The title of the presentation today is Data Center Thermal and Energy Optimization using the PUE, RTI, and RCI metrics. And I'm really happy to have with me today my good friend Magnus Herrlin, Magnus, I think we've known each other now for what, 100 years, I think? Have we known each other?
Almost.
Seems like it. For those of you who don't know Magnus, he's involved with the DCEP training, Data Center Energy Practitioner training. Many of you have been to his classes, and that was done with the support of the Department of Energy. And he's been involved with the national laboratories over the years, and he, like me, grew up doing computational fluid dynamics on big old hardware, big machines that took hours. And fortunately, machines are getting faster and things are going quicker, and it's become a lot easier than it was back when we both started, I think. So what we're going to be talking about is a data center. We've chosen one. I'll show it to you in a moment. In a sense, it doesn't matter what the data center is or what it looks like. Each one of them has an optimal operating point. Independent of how it's designed, it's going to have a point in which energy is minimized and thermal efficiency is maximized. And understanding where this point is important for a variety of reasons that we'll talk about, but it's important to know where it is. And today we're going to talk about how to find that point. Where is that point? So we're going to build a model. I've already done it. I'm not going to build it for you. It's already done. I built a model. The model I'm using is an adaptation of models I'm seeing come over my desk or come to my desk. I try to get involved with users, as most of you know. Many of you are my users. And I see an awful lot of data centers, and I see a lot of designs. One of the most recent ones that I see is a non-raised floor data center using fan walls. It's a popular design. And I'm going to be using sort of an amalgamation of that design that I've seen from other places. And then we're going to take it in its form, which is unoptimized, and we're going to optimize it for airflow, supply, air supply, and then we're going to tune it, essentially, thermally, to try to find its optimal operating point. Interestingly enough, this operating point will be minimal for energy, generally, and also best for thermal efficiency. So I'm going to review a little bit here of some of the work that if you've been to the DCEP training with Magnus or others, they'll teach you about air management. I'm going to do a little of that here. I'm not going to go over it in great detail, but I'm going to do a little of it because we're going to be using this terminology. So we're going to be using the terminology of recirculation and recirculation is one of the words we'll be using, and bypass, okay? So recirculation is when you have an IT rack and the air is coming out of it and going back over the top and getting sucked into the intake. This is what we generally refer to as recirculation. A bypass airflow is the other problem, where you've got too much air and it goes by the racks. Both of these are bad. In the recirculation case, you're breathing your own hot exhaust and you're going to get hot spots. It's just bad news. And that's generally a result of the fact that you're not getting enough supply air. But bypass is also bad because bypass tends to heat up the exhaust of the returning air back to the air handlers.
And they cool down.
They cool down, that's right. And the issue with return air temperature being hot or low, what you get in bypass case is their efficiency goes down. So, right, because the delta T is, heat transfer is maximized when delta T is highest. So you want the biggest temperature differential between return and supply on the cooling unit, and that gives you your best efficiency. So, importance of air management. It's both thermal and energy important. I mean, on the thermal side, you want to ensure that your servers are operating at the right temperature range. And ASHRAE has It's not specified. It's actually not a spec, is it, Magnus? It's recommendation, is it? I know that they get sensitive about this, but it's a recommendation.
Yes, it's really a guideline.
That's right. It is a guideline. That's right. But we treat it like a spec because people want to be within it. So it's treated like a specification, but it's really a guideline.
It really became like a de facto standard, if you will.
That's correct. The other point that's becoming more important these days is energy management. Magnus, I was reading recently, as you have probably seen as well, all kinds of chatter in the press about data center energy consumption, and now they're talking about it being 6% of all generated electricity in the world.
Mm. Yeah, I saw that. I think they're a little bit inflated, these predictions. We just at Lawrence Berkeley National Laboratory, we're developing a new report for Congress. Mm-hmm. And the people are writing that report. They're very skeptical to this, disaster predictions going into the future. But I think it's going to start to increase again. Yes.
It's flattened. I saw it flatten. I grew up building computers, so we ran at very, fairly high voltages. And to get the power down, they dropped the voltage of the switching on the transistors down, and that flattened it for a period of time.
Right.
But I think it's rising again. So energy will continue to be an issue for us in data centers as it is in our everyday life. The other point is capital, and this is the data center itself and the cooling equipment associated with cooling these systems is important. And here I'll point out a couple of things. One, just the capital cost itself, the upfront cost, but also the operating cost and life cycle cost. Mm-hmm. Here, Magnus, what I'm referring to is that if you run these things at low supply air temp, it just beats up the chiller. Yep, it really does, and they don't last as long. So running them as hot as you can will provide for longer life cycle on the cooling equipment. Is the point. Okay. So the goals are to run as high as you can in supply air temp with as little air as you possibly can on the supply side. In other words, only give the IT servers what they need and not more. And you get better chiller efficiency, reduced fan energy. Fan energy is important, and we'll talk about that. You meet your server requirements and you enhance economizer utilization. A lot of economization going on right now where you're basically taking outdoor air temperature and supplying it to the servers. And we see this in chiller design or cooling design. Sometimes they use evaporative media to do this. Sometimes they're just using dry air heat exchangers where they're Magnus, I don't see so much what we used to call free air, where they bring the air directly into the data center. I see dry.
I think it's still around, but I mean, here on the West Coast is an ideal
it is.
Location for air-side economizers. But the problem with air-side economizers is that usually you have evaporative air cooling.
Yeah.
And as you know, we don't have much water in the Southwest, so that's becoming a challenge.
Yes. And dry coolers are the idea, dry economizer coolers are the idea of just using a heat exchanger out there, putting a lot of surface area outside so you can take advantage of the temperature without having to use a compression cycle. So, but the point is that if you run with a higher supply air temp, you open the window for the economizer to operate. In other words, it can operate over a greater range because your supply temps are higher. So now let me also just talk about a couple other metrics I'm going to be using today. The first one is RTI, and Magnus had a lot to do with this. I'm going to give you the credit for inventing it. Did you invent it, Magnus?
I guess.
I think you did. So I like it. I always liked it. I liked it the first time I read the paper. I liked it back 100 years ago when you and I were young. And really, I like to look at it from a flow rate. You can look at it from a delta T point of view, but essentially, I like to look at it from a flow rate point of view because I'm a flow guy. So in the numerator, we've got rack demand. This is what the racks want. And we'll go over sort of how we get to that point in a moment. And down below, we have what is being delivered. And you want these things to be very close. You'd preferably like them to be equivalent, because if they're equal, that means that I don't have any bypass airflow and I don't have any recirculation. So again, the reason I defined those terms. I don't have the racks recirculating on themselves, and I don't have the air handlers pushing by the racks and contaminating the return airflow with low temperature. So that's really the important one, or one of the important ones, RTI. And we have a range in percentages. So as you can see, this is a ratio. So 100% is perfect. Greater than 100% means this guy is over delivering, and you're getting, whoops, I'm sorry, I went the wrong way. Over 100% means that you're not delivering enough. And what happens is you get recirculation, and less than 100% is you're supplying too much of this in the denominator, and you're getting bypass airflow. The air's got to go somewhere. One of the things my users always forget: conservation of mass. It goes somewhere. The air has to go somewhere. It can't just stop. So just a note about that. Now, the other one we're going to be talking about is RCI high and low. And this is a way to use a metric to predict whether or not the racks are within the acceptable range of thermal temperature. Or another way to say it is, how much are they in compliance? Is that fair, Magnus?
Yes, I think that's fair. And you might think that this is a little bit complicated. These definitions require some further knowledge maybe. But the reason that it looks a little bit complicated is that this metric does not only look at how many intakes that are above the recommended range, but by how much.
Right.
And that is very, very important, because imagine that you had a situation where a few points were right at the maximum recommended, and another case where they are like 10 degrees higher than the maximum recommended. That's different, right? There's still just a few points above the recommended, but the difference is that in the second case, they are much above the recommended range. So that's going to give another RCI value.
Correct. So it takes into account quantity and magnitude both of these numbers, and that's one of the reasons I always liked it. It gives you in one metric both quantity and magnitude. So we're going to use these to model a data center or to review a data center. So the way we'll do it is to build a model. We've already built it. We're going to use CFD to build it. We're going to use CoolSim. And a few notes about creating data centers. Just again, for new users or my users, avoid small details. It is not a CAD system. One of the things that I run into with new users is they want to put everything in it, and you can learn a lot with a fairly coarse model about what's going on in the room. You don't have to put every little tiny thing in the model. If later on you want to add details to see if they make a difference in the results, it's easy to do. So focus on the big stuff. Focus on, where are the inlets? Where's the racks in the room? Of course, where placement is important. Height of the room, supply plenum placement, supply plenum depth, return depth, placement of racks. But when it comes to the rack itself, average watts is a good place to start. Oftentimes it's all you know anyway, because you haven't built it yet. You have no idea where it's going to be in the rack. So you have to use some kind of metric, and average watts works fairly well. Later on, if you want to tighten it up and put the watts specifically in the rack in a certain vertical location, you can do that. But to get started, just go with average watts per rack would be my recommendation. Get your hands around the big parameters in the room. And then use that to determine the overall optimal operating point. Here we're looking at rack load versus air handler delivery, flow rates and temperatures. And I want to remind people that the governing equation for all of this stuff is here. It is the convective heat transfer equation. Heat mass is equal to mass flow rate times the density of air times the specific heat of air times delta T. That's true for the racks, true for the air handler, true for everything in the data center. Understanding these things, and by the way, this turns into a constant at a given altitude, so that's just a constant. So it turns into really flow rate and delta T is equal to Q. Okay. Now, we're going to use another metric as well, our favorite, PUE. And PUE is total facility energy over IT energy. Not my favorite metric, to be honest, Magnus. We have in the numerator total facility energy, and that's everything plus IT. So you've got everything. You've got breaker panels and distributor wiring. You've got chillers and heat pumps and fans. I mean, it really, in its base definition, includes everything. And plus IT equipment in the numerator too, divided by IT energy. However, most of the stuff on the left is dominated by chillers and fans. So it's really, you know, the IT equipment compared to chillers and you know, fans, that ends up being 75% of it. The cooling system makes up 75% of the non-IT load. Everything else is really a second order effect. So if you're really looking to drive efficiency of a data center, it's really just the ratio of cooling power plus IT energy over IT energy. Now, just a note here about this relationship. The ASHRAE is working on a specification called 90.4. It's called mechanical load component, and they take out the IT energy in the numerator and they just compare these two, which I tend to like better. But PUE is broadly used. It's very popular. And you can see here that if I matched it perfectly and took out the IT energy in the numerator, we'd have you know, I'm sorry, took out cooling power. If I took out cooling power altogether, I'd have a ratio of 1, right? So lower is better. And as this number rises, as it goes up, then the PUE goes up. It goes up to, you know. In fact, if you had a PUE of 2, it would mean that you've got 1 here and 1 here compared to that, and that means the cooling power is equivalent to the IT energy power.
Maybe we should mention here, Paul, that as most of you probably know, PUE was invented by the Green Grid, but they have now handed over to ISO, an international standard organization, and PUE is now an ISO standard, actually.
Yeah, it's unfortunate. There's problems with it.
Right.
You and I both know. For example, IT energy has got the fans in it, right? So for the IT equipment. So and all there's other issues, you know, if the room's not heavily loaded, if you built a big data center but you only partially load it, then your PUE is going to go down. So it has its own set of issues that are being addressed, I think, by ASHRAE very slowly, but nonetheless.
Right.
So the cooling system energy is made up predominantly of the heat rejection system. People often get confused when I say the word heat pump, but that's what it is. A chiller is a heat pump. They're all heat pumps. They're just moving it from one place to another. And the coefficient of performance for a chiller is the ratio of the amount of heat you're dumping compared to the work you're doing. Typical COP for chillers is, you know, 2, 3, 4 if you're lucky. They always measure it in the United States. They always do kilowatts per ton, right, Magnus?
Yeah, exactly.
Talk about mix your units. But if you neutralize the units, it ends up being somewhere around 3 or 4 on a good day for a typical chiller. So thermal load in the room compared to the energy to remove it. I tend to think of COP as for the data center itself, which is more like an MLC kind of calculation. So, okay. So, and chillers in the range that we tend to work tend to be fairly flat. I mean, this is a approximation as well, but you can think of this as approximately 2% per degree F of efficiency improvement. So as you raise the return air temp or the chilled water temp, leaving chilled water temp, your efficiency increases. And this is just what we were saying before about, again, delta T. If the temperature coming out of the data center is high and your atmosphere is fixed, then that delta, the bigger that delta, the better the overall efficiency is, just again, due to the heat transfer equation. It's fairly straightforward, but it's powerful. And And if you run at high supply air temp and therefore high return air temp, the opportunity to use an atmosphere that is, nominally ambient temperature increases. In other words, the economizer gets better because the window of opportunity for that, in terms of temperature, for that economizer to operate widens. So you want to run as high as you can for your chiller set point. I also want to remind people that fan power is very important as well. It's a cubic relationship to RPM or CFM, whichever you choose. So changing the CFM down just a little will reduce horsepower a lot. So again, the reason we want to run with only the amount of air we need to satisfy the demands of the racks is because we can save a lot of energy in fan, and we ultimately run with a higher return air temp. So, yeah, okay. Now, steps we're going to take to optimize this data center are, first, determine how much air we need. A fairly good rule of thumb is 125 CFM per kW. This number has been coming down recent years. You've seen Magnus as well.
Yeah.
It used to be, if you remember, it used to be 156 was always the number we used.
Mm-hmm.
And you're teaching a course now on IT as well, and part of your DSUP training, right?
Yeah, that's the latest, and that 25-degree delta cross service is creeping up because of not that the service providers are so concerned about us on the facility side, but they have problems to push more air through their servers, and the way to go around that is actually to increase the delta T across the servers, and that's what we see.
Right, and the chips are getting more tolerant, and the heat exchangers are getting better on the chips themselves.
Mm-hmm.
So 125 is actually now a fairly conservative number, as Magnus just pointed out. They're often going to 100 on this. So if the math is easier at 100, just think of 100. But it's a fairly good rule of thumb. And what you're trying to do is match what those servers need. Now, to be frank, none of us know exactly what these servers need. I think we should be honest here, Magnus. These are all control systems done by somebody with a proprietary control loop system, right?
Mm-hmm.
But we know from the heat the equation for convective heat transfer that we need at least this much. That if we're going to dump, a certain amount of heat at a given altitude, then we're going to need at least this much air. Mm-hmm. It may be that you need a little more because the servers may be pushing more than they really need, but we need at least this much. So it serves as a good baseline for us to move forward.
It's a good baseline. Something else that we could probably emphasize is that depending on what kind of air distribution system you have in your facility, for example, if you have a raised floor, you generally need a little bit more supply than what's drawn into the servers. But on the other hand, if you have an overhead system with diffusers, then there's opposite. You might not need so much supply air because when air is coming down into the aisles, you get this entrainment of air already in the data center. Yeah. So it depends a little bit what kind of system you have, air distribution system you have.
That's right. And on air supply temp as well, there is a point where if you get too high, the servers will start to kick into overdrive on their thermal control system and ramp the fans up, and then you're losing. And that number that is often referenced is 77F. And I apologize to my international community who's all going, what is F? What's with the F? But we're in America and we use Fahrenheit. But right around 77, the thermal systems in the server start to ramp, and you begin to lose your, I would say, advantage.
So maybe I can add something that we just have updated our training program, and so we found that this effect of a server or the fans in the server speeding up, that effect is almost marginal compared to the savings on the chiller side. it's almost a factor of 10 difference. So so we shouldn't be too concerned about that, actually.
Okay, that's good feedback. It goes to the point of, hotter is better, really. Again, back to keeping the okay, so optimization steps, we're going to adjust the airflow until our RTI goes to 100, and then we see RCI high beginning to decline a bit. We're going to implement air management as required. Then we're going to drive the supply air temp up until RCI begins to go down a little more, because we know we're going to get good efficiency out of that chiller if we can get it up. Again, here's the actual relationship, 1.8F or 3.5%. That's generally what you can get. Again, a good rule of thumb. And this is the data center we'll be using. This is a data center. It's an amalgamation, I said, of stuff I've seen recently. This is a hot aisle contained design. You see the racks here on the front. This is the containment here. It's got a ceiling plenum return back to the fan coils. These are what generally are referred to as fan walls. It is the entire surface of both sides in this case. I've seen them with one side, I've seen them with both sides. In this case, both sides are dumping heat into this room. The room is about 20,000 square feet. It's not that big, but we're dumping nearly 7 megawatts into that room. Our density is about 310 kilowatts per square foot. So this thing is pretty well packed. That's what I'm seeing. It's got a large return plenum, 14-foot return plenum to get all that air back. But it's very common from what I'm seeing. I see a lot of these. What's happened is raised floors are not as popular anymore simply because of the volume. You've got so much air that you're trying to move into that room. I'm seeing rack loads here, Magnus. It's not unusual to see them. I've seen designs with rack loads in the 40 kilowatt range per rack. I mean,
absolutely.
We're just seeing some crazy numbers. And it is related to artificial intelligence, I think, part of it, because they're all using GPUs. But it's also just more, So the first thing I'm going to do here is show you this chart, this set of gauges here. And this is kind of fun because Magnus and I, as I mentioned, have known each other a very long time, and he presented a paper back in, Magnus, it was a while ago, I think, wasn't it, where you presented this?
2005 and 2008.
Yeah. Is it 20 years ago? And he put together a paper and he said, listen, we've come up with these metrics, and really what you need is a dashboard. You need a little bit of a dashboard with gauges on it so people can understand what's going on by looking at one shot. And I thought it was great. I thought it was a great idea. In CFD, we always get all excited about our beautiful color pictures and our beautiful, flow diagrams and flow path lines and things like that. And I'm going to show you some because I can't resist, of course. But this method right here of being able to look at 4 gauges, essentially, and have them color coded to understand what's going on in this data center, I think is very powerful. So here we have PUE, RTI, RCI high, and RCI low, all displayed at the same exact time on a chart. And this is going to be part of CoolSim. And the CoolSim output report, I'll show you in a moment, we're including this. We're generating this for you automatically. Okay, so you'll have it. So PUE is 2. So I told you, Magnus, I'd detune this data center to make it look not so good. So PUE 2 implies that for every kilowatt we're putting in that data center, there's another kilowatt required to get it back out.
Yeah.
And you and I have seen data centers like this. We've seen them worse than this, where it's actually we're spending more money on cooling than we are on IT. But what's this telling us over here, Magnus? RTI 78.7.
Yeah, we have too much air into that facility.
Yeah, that's exactly right. So we put it right in here. We have bypass air. On this side, it's bypass airflow. On this side, it's recirculation. Just way too much air. 20, 30% more air than we need. RCI high, well, it's 100%. We don't have any problems with temperature because we've got so much air. And RCI low, oh my God, 25. So we're way off. Now, I'm going to, this is a hyperlink. One of the other things we've done in CoolSim recently is we have a hyperlink feature. So I click on that image and up comes the entire report for CoolSim, which just to, by the way, I didn't mention, but if you have any questions as we go, please go ahead and put them in the question block. Over on the right, there's a opportunity for questions. And what I can do, as soon as I can find it here, is I'm going to also put this information in chat so I can share with you. Let's see, send to all. So I can put in the chat box as soon as I find it, the opportunity for you to see these plots as well. I don't see it offhand, so I'll do it in a moment. But this is the CoolSim output report right here, and we're looking at it on the web. And this is how it's organized now. You see right here is the energy report with those plots in it. And then over on the left are all the 3D plots, and these are all, this is all numerical data over here. So let's first take a look at our rack inlets, because this is the one that we always look at. This is the, we call this a Visine chart sometimes. Of those of you who are old enough to remember, I'm dating myself again. Visine used to do a commercial. I have to explain my jokes. Visine used to do a commercial where if your eyes were red, you put the Visine in and they called it get the red out. So here we're getting the red out. So this is called the Visine chart. And you can see it's not, there's no red for sure. We got a lot of blue. We're way below. And this is a compliance plot. This is the ASHRAE recommended temperature. So the way this one works is that if you're above the 80.6 recommended inlet temp, it'll be red. If you're below 64.4, it'll be blue. So we're way below. And that's why our RCI low is reading the way it is that we're too low. And we've got some in compliance, but not very many. Now, let me show you also the Pathline plot here. These CFD results really just emphasize what we've already seen in the chart, in the metrics. We've got too much air. There's just too much air coming into this room, and it's getting into the returns. You can see some of the Pathlines getting into returns here. There's just too much air in the room, and it's blowing right by the servers and cooling off our return temps. Let's take a look at the CRAC performance. Watch the returns. Look at the delta T's here. We've got 16 degrees on the delta T's of the returns. It's just not good. You want that to be, remember, we've got our rack set at 25, and I'm seeing 17, 16. So we've got an average here of 15.77 on the delta T, and that's just not good. So we've got a problem with this data center. It's not optimized, and we've got to fix it, and this chart tells us that. With one chart, it tells us. So let's begin our optimization process. So here's case 2. Now here, RTI is 95.71. So the first thing we did is begin to drive towards 100% by reducing the amount of air coming from the air handlers. So now our racks are still okay, and we're still too cold, but at least we've got this down, and our PUE has come down, right? Because the fan law is cubic. So a little bit of change in fan speed on the blower will drive down your PUE, and lower is better. Because again, if it's 1, it means you've got the window open, you're not using any compression or any kind of mechanical cooling, you've just got the window open. In other words, the IT in the numerator is equal to the energy of the IT load in the denominator. So you want this as low as you can get it. So now I could open this one, but it's, well, yeah, let's open it. So we'll take a look at this, and you see here now our delta T's got a little better. We're at 19 degrees now, so that's good. So we're getting higher return air temps in general. And if we take a look at our 3D file here, in particular, there's a full range. We can take a look at full range here. And you can see things are improving on our rack inlets a little bit. Okay, so we've got more green now. But the other thing I want to show you is, yes, we've got some green, but RTI high is no longer 100%. It's come down just a little. I think, what was it, 98, Magnus? I think we just saw 98. So the RCI high is beginning to show us a little bit of this activity, where we're getting a little bit of a creep here.
Right.
And you can see 99.98, it has dropped. So if we look at them side by side, here's our base case over here, and here's our case 2, where all we did is reduce supply air. That's the first thing you want to do to balance, to reduce the supply air. And we did that, and what happened was our RCI high came down just a little. It's still pretty good, but it came down just a little. And our RCI low came up just a little. So that tells us that, you know, we're getting a little bit better. We've still got temperature problems. We're getting close to being optimized on the racks themselves compared to the air handlers, but we've still got some issues. So we'll take the next step here on this one. What does this one tell you, Magnus? I'll let you narrate this one while I search for the chat box window.
Well, now we can see that in the second chart up to the top right, the airflow balance is close to balanced. There is supplying as much air as that is drawn into the servers. And the PUE, of course, goes down, becomes better, because we get even more benefits from that cubicle fan law. And RCI will drop a little bit because, again, we're not pumping in as much air. And the RCI low is still high.
So yeah, so what we've done here is simply begin to raise supply air temp. And the problem is that if you don't manage your air correctly, these work against each other in a sense, right? Because we're getting close to being optimized on ratio of airflow, but our RCI high has dropped down to 88. We've got some hotspot issues and magnitude, but we're getting better. Now we've come off 0 or 50, but now we're good. We're out of that low end range. So let's go take a look here at our plots. And again, we'll go back to the same plots. I just hyperlink the online plots here, and here's what we have. Now this is a compliance plot. Again, we're looking at temperature range, and you can see we've got some issues. As we raise supply air temp, and we've got the airflow nearly balanced, we run into issues with temperature. And this is a result of poor air management. And the way we've modeled this one, if you attended any of my earlier webinars, what I've done here is I'm modeling really the server. What I've done here is the width of these racks is really the width of the server. And I've got leakage set between these racks, leakage parameter between these racks. It's really just a porous media. But let me show you what this looks like in temperature. So let's take a look at a 6-foot slice. By the way, this is a standard report. I have done nothing here except push a button to get all this stuff. CoolSim automates this all for you. But here you can see what we have is a slice. We've sliced it about 6 feet in this data center. We're looking at thermal, right? So let me whip this thing around with, this is a Y key. I'm going to turn off perspective, and you can see what's going on here. But what's going on is that I've got leakage. You can see the thermal pushing through this barrier out into the room. Because pressure is not uniform, right, Magnus? We don't have uniform pressure in any room. Right? A lot of people think but it's non-uniform. And as a result, pressure over here in certain parts of the geometry, you can see the air handlers here on both sides. So this is kind of a corner over here. You get like this, the air is going to come down. And by the time it gets here, it's leaked out into the hot aisle already. There's no air left for this region. You get a pressure differential over here. where the pressure in the hot aisle is higher than it is in the cold aisle, and it comes squirting right through. Either between racks is sensitive because, when you do hot aisle containment, it's the interface between the rack and the containment itself is important. Underneath the rack is important. I think I have these things 3 inches off the floor. Underneath is very important. And rack rails inside the rack between the server and the edge of the rack, on top and on below, blanking plates. It's all really important to create a proper seal between hot and cold. Magnus, I was working on one of these for one of the national laboratories, one of the smaller data centers, and they had sent me thermal data. And the only way I could get the thermal data to match this model data, the simulation data, to calibrate was to open up the leakage to almost 100%. And
right.
And I called them, and we did one of these reviews like this, and I showed it to them. I said, "You guys got to be leaking terribly." And they said, "Well, how did you know that?" Well, the temperature data told me that, right? That they were measuring temperatures out here. They're almost equivalent to what was over here, which means it has to be leaking pretty badly.
So I think, Paul, that this demonstrates the importance of air management, because this is nothing else than an air management issue. You haven't tightened up your equipment rows. So what we are preaching in our training program is air management is a prerequisite before you do other energy efficiency measures in data centers.
Exactly correct. That unless you have proper sealing on these designs, and these designs are critical. And by the way, this will happen also in other cases where you get a pressure differential. For example, if you have the chillers go down or fans go down on the on the air handlers, you'll get a pressure differential and it'll come leaking through. And the leakage often occurs here. And what I find sometimes is that the people I'm working with, Magnus, are the design community and not the people doing the IT implementation. So for those of you who are in colos or working for colos or doing this kind of work, it's really important to stress things like proper cable management, proper sealing around the rack, proper sealing under the rack, inside the rack. Make sure all the blanking panels are in place, because the integrity of the design assumes that you have proper sealing between the racks and the hot and cold. And no different than what we learned back, when we started working on IBM data centers a long time ago, right, Magnus? It hasn't changed. It's just that the density is now so high that this becomes more critical, if you know what I mean.
Absolutely.
Yeah. So there's that one. So we turned up temp. We've got problems. So the last step is air management. So what we did in case 4 is I simply went into that same design and reduced the amount of leakage that was assumed between those racks. That's all. That's all I had to do was change the percent area open. I had actually cranked it up to about 85% up until this point. And right here, I cranked it back down to 10%. 10% is a fairly reasonable number. I mean, there's going to be some leakage. Please don't build data centers with no leakage. I have customers who do that. Not a good thing, because first, it usually violates the law of conservation of mass, because the supply is not balanced with the demand by the racks. Second of all, it's not realistic. There's always some leakage. But here, all we've done is, you see the PUE is the same, the RTI is the same, near optimal. You want it to be in the 90s. The RCI high is near 100%, and I'm not too cold. So the only thing here that was done was we tightened up the racks. So now if I go back and look at that same image, we're going to see, well, it wasn't this one, it was a slice at 6. So here's a slice at 6. And you'll see here that now it's positive. Look, same region. Now there's a little bit of leakage here. I mean, there's 10%. So you're going to get some coming out, but it doesn't make it into the cold aisle. And the pressure differential here is sufficient to hold it. And that's a fairly good shot right there of what you see, you know, again, right here. I mean, the world isn't perfect. You're going to get a little bit of temperature gradient into the cold dial as you drive towards an RTI of 100 and an RCI of 100. So, you know, that is sort of the balance, right? Magnus, is what you would say?
Oh, yeah, absolutely. I mean, this looks really good.
The rest of it is, you know, we do pressure plots, and pressure plots are tougher, though. I find the pressure plots, you know, it depends on, pressure is a funny thing. It's a relative comparison. I tend to look at velocities a lot because, for example, here in a pressure plot, we're looking at max min. You can't see much contrast, so you have to start clamping it and tightening it in. CoolSim automatically picks the max value and the min value and plots color across. And you have to go in and tighten it up in order to get the same kind of contour and color that I showed you earlier. Yeah. And you see, let's take a look now at our delta T's. Ooh, that looks pretty good. I'm looking at almost a 20-degree delta T right there. Now, it's never going to be quite what the racks are. If we look at the racks, the rack cooling report here, I probably have a better delta T on the racks. The problem is there's so many racks. So we get down and, yeah, we don't actually calculate averages. I should do that. But you know, the delta T's, here's the return 96. So, you know, 20. So 20, you know, it's not quite 25. But the boundary condition was set, and then you numerically try to achieve it. So you'll see it be higher in some cases. Yeah. And you see it's all passing. So our Visine chart now looks good. Looks all green. Got a little bit of issue over here. We're out of compliance just a little bit on this back side. In all data centers, and by the way, when it's up high like that, it's probably not an issue because you probably aren't putting equipment up that high, or at least if you are, you know where the issues are. It's important to know where the issues are in a given data center. So again, we're looking at this data center. This is a top view. Let me turn on perspective here. And you see the air handlers are not symmetrically set. So these over here are offset. So this corner is going to be problematic. And it's really just geometry. It just has to do with the way the data center is laid out. And this is why, you know, average watts per rack and getting your racks in the right location and getting your mass flow parameters right and your temperatures right tells you an awful lot about the data center. From this simple work that we've done, we know that this section of the data center is going to be problematic simply because of the geometry of the room.
But is it fair to say, Paul, that this graph might overemphasize the problem because it's green or red, but in reality, that over temperature we see that the red areas, they are just marginally warmer than the rest of the room.
That's right. You are right, and that's why we also include this full range. So here's the full range, and full range takes, like you said, max and min of the entire room. And let me flip it around so we're looking at it the same way again. But here, same section. And you see that it's a contour. Magnus is right. And the reason we use the kind of the Visine chart is to sort of give you a quick look at where you are. We also include, of course, the full range, which takes max min temperature of the rack inlets and plots it with color. So you see here that it's not too bad. It's a little above. You can see the magnitude here. 80.6 is the number, and you can see we're a little above it. But you know what? These things are pretty tolerant. I don't think that's going to be much of a problem, to be honest. So that's why we include that one as well. And you know what's nice about it, Magnus, is the metric is showing that too, right? RCI high is 99 or 100.
I think what you have shown, Paul, is that you take your model, you just scan these diagrams that you've been showing, like this one that's on the screen now, and then you make a change and you see if the needles go the right way. And then when you reach a point where you think you have it pretty good, you dive into the details in your charts and your diagrams, and you understand much better what actually is going on when you look at individual racks. So isn't that really the process here?
Yes, it is. It absolutely is. And it gives you insight. So here on the last slide, what I've done is I've put all 4 cases together. This was something that Magnus recommended during the review that we did together, and I think it's a very good idea. So here's my base case, just to review. We were oversupplying here. By the way, I just put this presentation as a PDF into this system, GoToWebinar, and you can pull it. If you look at handouts on this little icon or little dialogue over on the right, you will see under handouts a link to a PDF, and you can download that. And that's this presentation. And by the way, each one of these I have hyperlinked to the full report. A really nice feature of CoolSim is this ability to share results using hyperlink now. So behind each one of these images, if you click on it, you'll get the entire report from which this picture came from, all its details. So you can kind of look at it that way. And it's also, for those of you who are generating this for customers, because many of you are in the design build field, being able to give them a 3D view of an image is really powerful. So this feature is quite nice. Just bury the hyperlink behind the image. But here in case 1, you can see we were too much air. We had bypass airflow, and 78, the RTI was 78, and the RCI high was 100%. So, we had way too much, but the racks were fine. RCI low was a mess. It was too low. Then what we did is we reduced the supply air just a little bit, and that helped our PUE, brought our PUE into shape a little better. But 2, it came down to 1.9, and RCI started to get affected just a little bit, not so bad, still too cold. Then we went up in temperature, and now the rack started to leak because we had air management problems. But RCI low came up, we got close in RTI, PUE 174, looking pretty good. So the final step was air management, as Magnus pointed out. Go ahead and fix the air management so that you're not leaking, things are sealed up. One of the questions that came in, by the way, ask questions at any point if you like. One of the questions that came in from one of my users actually, can you model gap in the rack? Yes, you can. We have a tool called Rack Builder, and Rack Builder allows you to put the equipment in the rack in a vertical direction, and it also allows you to put gaps in the rack. You can put a hole in it, literally, like missing blanking panel if you want. So the answer is yes, you can do that. So summary of the process: build it, be reasonable about the build. First, try to get your air management in place until you start to see a little bit of problem with RCI high. Then use air management techniques to improve those regions, and then turn up. Now we did this in just the opposite order. We turned up the supply air and then went after air management. It doesn't really matter, I suppose, Magnus, on the last part, the two orders there, but you sort of trade these two off. I mean, this is a balancing act between enough air and right temperature, right?
Yeah.
And then, yeah. So that's where we are. Look at this, 11:54, not so bad. We're coming up on the top of the hour. I have given you a copy of this in the chat box. There isn't a chat box on this thing. I don't know why. What there is a handouts page. So I put it in the handouts. So if you go to the handouts dialog, you'll be able to download it. The images are all hyperlinked. Yeah. And optimizing energy, yeah, it's just a process of iteration, trying to get the flow volume right, the supply air temp right. And the final part is here's air management. So CoolSim is an example of CFD coming a long way, I think, Magnus, from where we started back, when you and I started doing this work.
Oh yeah, definitely, and I think you've shown a methodology that we rarely see actually, that could really help the user to understand that energy alone is not enough now. We need to look at the thermals and CFD, of course. I did a lot of CFD modeling in my youth, so you can combine these two things. It becomes very, very powerful, and I think that's what Paul tried to show today.
Mm-hmm. So, Magnus, thank you for attending today and being here with us. Our contact information is here if you want to reach out. I think you've got a training coming up soon as well, right, Magnus? With some of this stuff will also be reviewed there, I think, right?
Oh yeah, it's coming up on. We're starting on May 13, and if anyone is interested to participate or understand what it's all about, you can send an email to that address that Paul has indicated here.
Mm-hmm. And you can reach me if you have any questions. I think we've reviewed most of the questions. I do have, there was a question here about other webinars and recordings. I do have on YouTube, I've put up a bunch of the stuff that I've done historically, and it's there if you want to take a look at it. Audrey asked me about a webinar on some more specific data center cooling itself, RAC, CFM Delta T, RAC positioning. They are there, Audrey. I'd have to, if you want to send me an email, I can point you to probably the one that's closest to what you're looking for. And when leakage, the question Michael Green had is, when leakage was repaired, I would expect the PUE to become more efficient. Is that a faulty assumption? Well, the problem, Michael, is that PUE is not that sensitive, unfortunately, to changes in things like that, because it's got IT in the numerator. It's got IT energy in the numerator. And the IT energy tends to wash out improvements you make to cooling energy. I'm not a fan of PUE for that reason. It's fairly insensitive as a metric. MLC is going to be much better, but it hasn't caught on. MLC just compares the energy to cool the data center to the energy required to drive the IT server. So you're getting more of a one-to-one ratio of, or a direct comparison of cooling energy compared to IT load energy. And so when you make a small change in MLC to things like fan or leakage or whatever, it will show up. It'll come up pretty quick. But PUE, because it's got IT energy in the numerator, it tends to not, the number doesn't change very much, unfortunately. But, it's better than nothing.
Another way to look at that is to understand that the reason that PUE didn't go down to the green area, that's the inherent energy efficiency or inefficiency of that selected cooling system.
Yeah.
If you, for example, introducing an evaporative cooling process, well, then you have changed the inherent energy efficiency of the cooling system.
Exactly.
And it will probably drop down in the green area.
Yeah, exactly correct. Yeah, I picked one that was kind of poor, to be honest. People talk to me, Magnus, about PUEs of 1.1 and so forth. The other thing about PUE is it's point in time, it changes. What you need is average PUE over the year, right? Because it's not constant. But yeah, you are right. If you change the cooling system to evaporative, or you add an economizer, it will change the PUE quite dramatically compared to, in this case, it was leakage. When we went from step 3 to step 4, we changed leakage. And so now what I'm looking at is average return air temp. Well, it wasn't leaking everywhere. It's only leaking in one small section of the room. Now, unfortunately, it was bad. It was leaking, so it was causing problems in one section of the room, but the average temperatures weren't affected that much. So it didn't really affect PUE that much. Yeah. Okay, direct free cooling with a proper filter could also reduce PME dramatically, of course. Yeah, direct free cooling is always with proper filters. Yes, you are right, Audrey, but you know, I have also been in data centers where it has rained because they're using free cooling. So, and that was at Princeton, by the way, data center, where what happened was the original design was fine, but it got out of whack over time, and the people who designed it went away, and they were bringing in some pretty moist air and hitting a dew point, and it was condensating on the racks. Not a good thing. So free air systems are great, but they need a control system, and that control system has to be tuned and maintained by the operators, and the operators need to know how to do that. So I don't see so much free air anymore. What I see is, I'd be interested in your take on this too, Magnus. What I see is evaporative cooling where you can get away with it, and also, you know, just big free cooler, dry coolers where you have large series of heat exchangers laying out there.
Well, I think dry coolers are becoming more popular or feasible because we have higher temperatures in our data centers these days. Yeah,
that's right. And you can get away with it. Yeah. Well, all right. It's top of the hour. I want to thank everybody for attending today. Magnus, thanks again. Great working with you as always. And I look forward to continuing our collaboration to teach people how to optimize data centers.
Thank you. I appreciate it.
Okay. Thanks, everyone. Bye now.
Bye.